This particular example comes from Robotics, and I'm following the work of Rob Grice and Valerie Peterson, but there's a bunch of related work by other people, but it's their particular description of this model that I'm going to be describing. So this is what we want to do is we have some robot made up of lots and lots of small moving parts, like that little robotic hand I showed that was on my cover. So we have something, it's a robot, but it has lots of little moving parts, maybe hundreds of them. And what we want to do is understand how those parts move in relation to each other and how we get the robot hand, say, from this position to some other position. Right? How's the best way to move, to reconfigure the robot from one configuration to another? Right? So rather than the robotic hand, which is a little too complicated for me to draw, we're going to work with a slightly simpler system. We're going to think of a robot. My particular robot in these drawings is simply going to consist of a bunch of hexagons in a plane. And what this robot can do is it has joints at the corners, has little joints. And any hexagon can rotate along one of those corners to a new position. Right? So they can freely, so this robot can reshape itself. I mean, imagine, I haven't drawn very many, but imagine lots more hexagons attached to each other. And this robot could shape itself into all sorts of different shapes by little hexagons rotating one after another along a vertex. Okay, so I want to rotate this green one into a new position. So you see what it's done is it's rotated across this corner into a new position, a single rotation. Right? So I'll call that R, that rotation. Now I want to rotate the purple one into a new position. Right? It's rotated upward into a new position. But maybe I want to rotate the green one and the purple one. Well, luckily, they're going into positions that don't interact. I mean, they're not going to run into each other. There's no harm in doing both of those rotations. And we could see that it wouldn't really matter if we did the green one and the purple one, or the purple one then the green one. We'd end up in the same place. And what's more, since they're not in each other's way, we actually could have done them both simultaneously. There's no reason not to go straight across from here to here and do them simultaneously. Right? So what's the natural model for this? The natural model for this is simply a square. So what's happened, if we go back for a second, whoops, is that our various shapes, our various configurations of the robot are now simply corresponding to single points. Each point is a different shape for the robot. The edges are corresponding to single rotations. And the fact that the square is filled in is a message that it's okay to go diagonally across and do them both simultaneously. Right? It's a statement that I can travel directly from here to here without having to do one operation at a time. All right? Okay, well, let's keep going. Maybe I want to move the green one again. All right, let's move the green one again. Well, if I move the green one again, I see that I get another square. And this square is adjacent to this square because they share two configurations, etc. I can move the purple one again, and I get another square, maybe down here. Or I could keep going. And each time I move something, I get some new piece that I have to add onto my model. Right? Well, let's make it more interesting. Now I want to move three pieces. I want to move the green one, I want to move the purple one, and I want to move the yellow one. Now, I'm going to move them in such a way that they don't run into each other, which means I can do whichever one I want first. In fact, I can do them all at once. And what do you suppose we get here? So the back face there was exactly what we started with before. And as we come forward, we see this one rotating into a new position. But again, because these moves are independent of each other and don't conflict with each other, we can go diagonally across this cube if we so choose, okay? Or in any way around or diagonally across. Okay, so we would represent this set of moves by a three-dimensional cube. And why stop there? We might have 4 independent pieces that could move as they wished, or 5 independent pieces, or 6 independent pieces. And of course, what are we getting is 4-dimensional cubes, 5-dimensional cubes, Now, I suspect everybody in this audience won't blink an eye at that idea of 4-dimensional cubes and 5-dimensional cubes, but just in case, let me just say that mathematicians really are just as happy in 4 dimensions or 104 dimensions as they are in 1, 2, or 3. Because of course, what all we mean by a cube here is just, well, I probably don't have to say anything about this to this audience, but I'll go through this slide quickly. So a 1-dimensional cube is simply a line segment. We can think of it as all the numbers between 0 and 1. A 2-dimensional cube is then any point in a 2-dimensional cube requires us to give 2 numbers, the distance along here and the distance along here. A 3-dimensional cube requires 3 numbers between 0 and 1 to give a position. Well, what's a 4-dimensional cube? It's just 4 numbers between 0 and 1. Or a 5-dimensional cube is 5 numbers between 0 and 1. So we can represent mathematically higher dimensional cubes are simply not a problem. Right? They're simply just as easy in higher dimensions as in lower dimensions. And not only that, using the idea of vectors, as viewing these things as vectors, we have a perfectly good notion of distance, angles, geometry, etc. in a higher dimensional cube. So geometry inside a higher dimensional cube is no problem. We know exactly what we mean. We know what the shortest path between 2 points is, how far it is between 2 points. We can do all the geometry we want in higher dimensions. Okay, so we can, going back to our robot, we take our robot, we look at all the different shapes the robot can take, we look at all the different ways to get from one shape to another by a single move, and we fill in all the squares and higher dimensional cubes which are allowed. In other words, in which there's nothing runs into each other, which are independent moves and one could be done simultaneously. All right? And we get some object made up of lots of cubes of all different dimensions, right, in which the points, the vertices, the nodes, represent different shapes of the robot. The cubes represent sets of independent moves, and now let's go past that. Let's go past that. What if we have a point here and a point way over here in our space? Well, now, if I want to know how, that corresponds to what? A shape of the robot and another shape of the robot. And now, a path between those 2 points corresponds to a sequence of moves that will get me from this shape to this shape. Right? So paths correspond to ways, choices of ways to reconfigure the robot to tell the robot how to change from this shape to that shape. And the distance between things corresponds to, well, time or at least complexity of getting from here to here. So if they're close together, it means I can get there very quickly, do all the necessary moves at once or whatever. And if they're very far away, it means it's going to take a long sequence of moves to get me from here to here without pieces crashing into each other. Okay? All right, so now we can see the geometry beginning to correspond to questions about the robot itself. Caution, as we go through, we're going to start talking about the geometry of these spaces in a minute, and caution, remember these things are not just a few squares nicely fit together. They can be very complicated. I can't even draw one that's complicated, but remember they can have many, many cubes, all different dimensions, fit together in all sorts of crazy ways, and just keep in mind that they may not be things that are easily drawn or easily pictured. Okay, so they're quite complicated. Even though the cubes themselves are simple things, the way they fit together could end up being quite complicated. Okay, I think they already sort of said this. The geometry can be complicated, but studying the geometry is an interesting and worthwhile thing to do because it can answer such questions as what's the most efficient way to get from one configuration to another? Are there several choices of ways, or is there basically one way to do it? How do we find that? How long will it take, etc.